Great, Yannick. Thanks a lot. So, hi everyone. I'm Rani Ettinger. I'm so happy to be presenting, speaking about how I've been using Spark and Ada in one of my courses. I'm working now since 2.5 years at NVIDIA on formal verification for software, mostly for C and C++ actually. But I'm still teaching, and I'm still teaching at Ben-Gurion University of the Negev in Israel, in the south of Israel in Beersheba. And I will speak about that course called Assertive Programming, and I teach some other mandatory courses using some formal verification too, like logic and automata theory. So for the course that I'm speaking of, it's Assertive Programming. It's an elective course given to third-year, roughly, computer science or software engineering students at Ben-Gurion University of the Negev. And it's mostly based on Rustan Leino's recent book, Program Proofs, and with most examples taken from Carroll Morgan's. So I have them here, actually. So Rustan Leino's book, Program Proofs, and Carroll Morgan's from the 90s, Programming from Specifications. Most of the examples I take from there after I've been teaching that topic for 8 years, starting 2013. And for 8 years, I've been teaching that as a 4-hour a week, two times 2 hours a week, times 13 weeks a semester. It was a bigger course on refinement. And I've since joining NVIDIA, turned the course into a shorter one that is the one I'm calling now Assertive Programming. I have 30 weeks of a 2-hour session each week. And I give this course twice a year. And in the lecture, I program and we verify correctness together in the classroom. And what I will try to do now is try to do the same. A part of lecture number 3, if I may. So just the subject, the title of the course, assertive programming. Of course, we are using assertions, assert statements, but I like on the first week of the semester to start this, to open the Wikipedia on the definition of assertiveness coming from psychology, I guess. And I like the idea of saying to my students, hey, you already know how to program. Most of the programs we program here are very easy. You know them from your first year. It's not a big deal. But I'd like to be able to argue for the correctness of the program, to be self-assured, no aggression, to be confident, to develop the communication skills, some critical thinking, hey, maybe there's a bug here, maybe there's a bug there, and some combination of the creative thinking of how to convince oneself, myself, others, and the machine that the program is correct, and to have effective communication, to develop the vocabulary, if you will, for discussing correctness of a program. And then there is, funny enough, in this definition, they speak of the confident declaration or affirmation of a statement without need of proof. And I showed that as well, that most of the semester we do try to prove correctness, but then at the edge we say, hey, time's up, let's not prove this, let's not prove that, let's formulate this in a convincing enough way to the human, because the human here is more important than the machine in this course. So let me take you through the third lecture of quick overview of the third lecture of the course. And in this lecture, we program, again, from Carroll Morgan's book, a simple program to find the square root of a natural number, rounded, if needed, down. So the natural floor of the non-negative square root of a natural number in a kind of a binary search. Let's see that. And let's see this program in detail. And what do I teach what do I teach about this program? I forgot that I'm on the other slide where I speak about the programs that I'm showing during the semester. They are really simple. Those are programs from Introduction to Computer Science or from Data Structures courses, really simple programs. Mostly iterative loops and loop invariants to prove correctness, and some recursion at the very end of the semester. Mostly integers, booleans, arrays, and then some data structures like binary trees and lists. That's it. So here's the, okay, so here I'm taking you to lecture number 3. I'll show you what they know already from the first 2 lectures. Then we'll develop a little bit. We will make the program partially correct, meaning that we don't know if it will terminate or not, but it will, if it terminates, it will be correct. And then we speak a little bit about termination. Okay. So we will have what's known as a total correctness. So, so this is what we want to find, the floor of the non-negative square root of a given natural number in logarithmic time. And this is the specification. So in Ada, since 2012 in the standard, you may already know it, there are, as part of the signature of a procedure, we can also annotate the program with aspects saying what is the precondition, what is the postcondition, what do I expect to know of the input when I start running this procedure, and what is the developer obliged to come up with the output that will satisfy some requirement. In this case, we get an integer number with a precondition that it's not negative, and we need to come up with an output parameter that's the square of a is, or that n is in between a square and a plus 1 square. So it's the rounded down, the floor of the square root of n. And we don't have to worry today about overflow, potential overflow, because we deal with big integers. That's nice to have. And on a later session, one could discuss, it's very important to discuss how to avoid overflow. Here's an implementation from the first couple of weeks. What we see here is, well, a procedure implemented, but there is much more than the implementation here, actually. There's some executable code, like initializing the output parameter a to 0. By the way, Yannick, can you see the mouse symbol, or should I use some laser?
Yes, we can see it. We can see it. It's
great,
small,
great.
We can see it.
Okay, thanks. So yeah, we initialize a to 0, and then in a loop we increment it by 1. But there's a lot of other stuff here going on. It's not something that should be executable code. The assertion, it can be verified dynamically at runtime, but when we use GNATprove with Spark, with the tooling, we can prove statically at compile time that the program is correct. So the assertion can be proved by GNATprove at compile time, kind of realizing what it's the vision of not Tony Hoare, but before him even Robert Floyd, from this 1967 or so, saying we need to have a verifying compiler. The compiler that at compile time will verify that the program is correct. Correct according to what? According to the specification that we shown here. So we have here so in the first 2 weeks of the semester, we learn how to call lemmas, or ghost procedures, here in 3 different places. I will show them, like the post condition. We say that when we exit the loop, a will be correct. A will be, a square will be below n, and a plus 1 square will not be below n. So it will be above n. So the post condition holds. So it's nice to demonstrate this as a kind of implication that if it holds here, then the program is correct. But for that, we need the initialization to be correct, so that the loop invariant will hold on entry to the loop in this case. So we prove that here, and need to show that when incrementing a in the loop, we are preserving the lemma, the invariant, sorry, the loop invariant. So we learn how to do that here on the first couple of weeks of the semester. And then on the 3rd week of the semester, we say, okay, let's come up with a logarithmic time, more advanced, more faster solution. And use the same ideas, just more and more. So throughout the semester, I teach more and more examples with more and more techniques of how to define the loop invariant and how to prove correctness. So here, let's see the design of a loop without the loop body yet. So the idea here by Carroll Morgan, I just rewrite it here in the classroom, actually in Dafny, and then I show them in Spark later, what I'm showing here. So the loop body is not yet implemented here. It will be later. But we already see that the loop invariant here we introduce a new variable b, and we say, okay, n will be somewhere between a square and b square. And gradually we'll bring them close together until they have a distance of 1, and we found our answer. And there's a lemma here that says, yeah, if we reach the end, everything will be fine because the invariant will hold, and the negation of the loop guard, it's called, will hold when we exit the loop. So b will be a plus 1. If we substitute b in the invariant with a plus 1, we get the post condition, and we're done. So hopefully this is a good design for the loop. Now we need to see that the initialization here, that a becomes 0 and b becomes n, is a good initialization that establishes the invariant. And actually it's not. So let's see what does the lemma mean, the procedure that is ghost. It means we will not introduce this into the executable code. At verification time, we try to see that for all big integer n, if it is greater or equal to 0, then the invariant with substitution of a by 0 and b by n will hold, meaning that n will be smaller than n squared. That's not true everywhere. It's not true for 0. It's not true for 1. So this is not a good initialization, and GNATprove will tell me. So I will try to fix it. I will prefix it, for example, as Carroll Morgan suggested, to initialization of b to be n plus 1. And then it will be fine. So we have a good initialization. We have a good post condition, good initialization. Let's dive into the loop body. In the loop body, yeah, so this is correct. Now GNATprove agrees with me. And this is what the meaning of the null here is. The null in the loop, in the procedure body, and this is a ghost procedure, tells GNATprove, can you please try to prove that this is correct by yourself? If not, I will help you here. Instead of null, I will write something. And it does. It manages. So that's nice. So let's design the body of the loop, the idea, each time to find the middle point and update either a or b, the lower or the upper bound. Here's some code, but following Carroll Morgan, I'm showing in this lecture, the third lecture of the semester, how we can derive a portion of the code by the proof obligation. So we say, okay, let's define m to be on each iteration, the middle point between a and b, no need to worry about overflow in this case. And if some guard will hold, and we don't know yet what this guard will be, actually, we will update a to the middle. Otherwise, we will update b. And by what we've learned in the first 2 weeks, we know how to specify those two lemmas. And let's look. Let's derive the lemma specifications. It becomes one of them. Lemma for updating a says that we know that the invariant holds, we know that the guard of the loop holds, b is not a plus 1 yet. We know that m is the middle point. We know that some unknown yet guard holds. So we reach the then part, and we need to know that the invariant will hold, but not for a and b, but rather for m and b, because soon we are going to assign m to a. So that's Tony Hoare in the late 60s taught us with substitution how to derive such proof obligations. And so I'm representing it here. And then I'm going into more details. I think SPARK is, GNATprove is good with this. Yeah, I think it's good with this, but let us try to be convinced by ourselves. This is what's really important for me in the classroom. So here are the details. With assertions, we recall from the invariant and the precondition what we know. I give them some names here. And we recall from the post condition, sending m to this invariant instead of a, that this is what we need to know. The second portion is already known, but this is missing. So we say, hey, this is missing. Let's try our luck and define this as our guard. So if m square is at most n, let's update a. Otherwise, update b. And GNATprove tells me, yeah, that's good. So I'm deriving the guard. Here is our guard. I even replaced the original code here. Instead of calling that function, I just put it in line here. If m square is at most n, and I update the lemma, and everything's good. But then I have to see, what about the other lemma? Is updating in the else branch b to m still good with this guard? And I look into the details, and I find now that, oops, sorry, clicking the wrong button. I find that, wow, by luck, what we need to know that a square is at most n, we know already from the precondition of the lemma, and what we need to know that n is strictly smaller than m square is actually a different way of saying the negation of that guard. And why did we arrive at the else at this lemma? Because the guard did not hold. So that works. And GNATprove is happy. Everybody's happy. Oops, I'm so sorry. I clicked the wrong button again. And where am I? I will do this to go back here. Great. So we are good to go. We have a running program. It's actually a correct program, and it's verified. So it's wonderful, but it's not perfect. The reason it's not perfect is I neglected to tell GNATprove to consider termination. It's my fault. It was my choice. I left it for us as humans to add to the explicitly to the lemmas the consideration of termination, the way I've been taught that by Carroll Morgan and others. So let's see how it affects us. So in order to see the tricky thing about termination, let's consider if we didn't assign m to be a plus b at the middle point between a and b. If we assigned it to be a plus 1, actually, this will be again linear search, like the close to the program from the first couple of weeks. If we assigned m to be at each iteration b minus 1, it will be a slower search. Again, linear search, but linear in n instead of linear in the square root of n. So that's slower. But what will happen if we assign m to a? This will be an endless loop. M will be a, m square, like a square here, will be at most n. We will update a to m, and then m to a, and then a to m, endlessly. So it's a non-termination. And GNATprove, I didn't ask it to prove termination, so it doesn't know about that. It's not its fault. It's my fault. So manually, let's do something about it. Let's update the lemmas. And how do we do that? It's what's known as a instead of invariant for the loop, it's a variant for the loop. It's an expression that decreases at each iteration. It's an integer expression that decreases at each iteration, but never below some lower bound like 0. So we say it here. Where do we say it? I'm just saying here that everything verifies because we didn't look at the precondition that m was a plus b divided by 2, or that n is b. We didn't need it here. So fixing it, let's try to avoid this problem. Add the decreases, it's called, decreases or increases, in our case, decreases related assertion, and fix into the assertions, into the proof obligations, the claim that each iteration brings us closer to termination. And when we say it this way, we say, well, you know, m minus the difference between b and a is going to decrease at each iteration. B minus a, here I take backup, call it conventionally v0, the variant at the beginning, b minus a, and we add another assertion at the end, not only at the end of the loop body, not only that loop invariant still holds, but that was maintained, but also the variant is smaller now. And after some substitution here, it becomes those parts of the proof obligation, and they are not, it doesn't work. I can get even a proof counter example showing me that with negative numbers, this will not work. So, okay, so we need to fix this. We need to tell the program that a and b are not going to be negative numbers. I forgot about that. So let's fix that. How do I fix it? Okay, there are different ways to fixing this. I will show just one, how to avoid such situations. So what we do is we strengthen the invariant to make the lemmas clearly provable. So the lemma said that the numbers could be negative, but in our original program, it would have not been the case. The lemma doesn't know. It knows only its precondition and needs to show that it implies the postcondition. So that's the goal of me. In the invariant, I can strengthen it this way, say, don't worry, A is not negative, and B is larger than A, and then everything becomes fine, the proof holds, and the other proof proof obligation works. And then we go back to the original code and re-verify that the first two lemmas for the initialization and for the post condition, they also hold for the updated lemma, loop invariant. This is why I like to put the invariant in a predicate, in a function on the side, so that when I change it during the development, I don't have to worry about rewriting many assertions and lemma specifications. And now it works. So we have a working program. It's a totally correct program. It's been proven by us. GNATprove helped me, but we know to document the proof obligations. And that's the code. Eventually, that's the code we reached. After removing all the annotation, we like to do that at the end. Remove, because my students always complain, why do we need this assertion? Do we need that assertion? Do we need that lemma if GNATprove or Dafny tells me that it's correct anyway? Yeah, we do, because it's not a Dafny and not a SPARK course. We like to know by ourselves why the program is correct. But at the end, it's nice to end this way with showing the code and seeing, this is what we developed. Cool. And so some takeaways from the course. What do I hope the students at the end of such 13 weeks of 2-hour examples will be able to do with some exercises? So some like a heavy weight, 80% of the final grade, final assignment. After that, I hope they will know to be able to specify them by themselves, preconditions, post-conditions, ghost code, loop invariants, variants, assertions, sometimes assumptions, as in order to be sure that their proof goal is on the right track, and to be able to know, as said, what the proof obligations or what the tools call verification conditions are, and how to decompose a program into sub-programs and specify those sub-programs in a way that will help us eventually end up with correct code. And then just the main goal is become assertive. So some examples of exercises I give. And I will end in a couple of minutes. So I give them examples in exercises of well-known documented SPARK programs. And I redevelop it in Dafny and tell them, go ahead and verify it. Go and read the blog post to see how they verified in SPARK, and then and port the proof to Dafny in a way. And then I give them some other assignments. And if I have any criterion of success for this course, first of all, many of the students get really frustrated with their assertions. Why do we need so many assertions? But on the other hand, at the end, some of them really develop not so trivial solutions with proofs and all that. So I'm really happy with that part. And then we learn how to prove the lemmas. Sometimes if the lemma is not proven by the tool, we need to try hard to convince the tool. And there are some things there that there are great things in SPARK that I love. I love the you know that I show them the GNAT Studio, where it shows me the proof obligations in a different way. So I really like that. We don't have that in Dafny, so that's very nice. On the other hand, I have some ways of hinting for the reason for the correctness of specific properties in lemma proofs in Dafny that I don't yet have in SPARK. So hopefully we will have them one day. And multiple assignments are really convenient from the literature, but also in practice. And we have them in Dafny. So it will be nice if we have them one day. So finally, if Rustan Leino always says program safely, I will say also program assertive.